Deep within the unfathomable cores of neutron stars, a substance so bizarre it defies our everyday understanding of physics might be lurking. It's known as strange matter, and it possesses a truly terrifying property. It's theorized to be a perfectly stable form of matter, more stable than anything else in the universe. This stability comes with a frightening consequence. If it were to come into contact with ordinary matter, it would trigger a catastrophic chain reaction, converting everything it touches into more of itself. Imagine a single microscopic speck of this material, a strangelet, making its way to Earth. If it touched our planet, it would begin a relentless process of conversion, transforming the entire Earth. From its core to its crust, into a hot, dense lump of strange goo. This isn't just science fiction, it's a possibility rooted in the complex physics of quantum chromodynamics. So, what exactly is strange matter? And how could something so small possess the power to destroy an entire world? To understand strange matter, we first need to look at the fundamental building blocks of the matter we know and love. Everything around us, from the air we breathe to the ground beneath our feet, is made of atoms. At the center of these atoms are nuclei, which are composed of protons and neutrons. For a long time, we thought protons and neutrons were fundamental particles. But we now know they are made of even smaller components called quarks. There are different flavors of quarks, and the ones that make up all the stable matter in the universe are the up quark and the down quark. A proton is made of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. These are the ingredients for the reality we experience every day. But the standard model of particle physics tells us there are actually 6 flavors of quarks in total. Besides the familiar up and down quarks, there are also charm, strange, top and bottom quarks. These other quarks are much heavier and highly unstable. They only appear for fleeting moments in high-energy environments, like particle accelerators, before rapidly decaying back into the more stable up and down quarks. The strange quark is one of these exotic, heavier flavors. So, if strange quarks are so unstable, how could they possibly form a substance more stable than anything else? This is where the concept of the strangelet comes into play. The idea was proposed by physicists Arnold Bodmer and Edward Witten, who explored the behavior of quarks under extreme conditions. They hypothesized that under immense pressure, like that found inside the core of a neutron star, something extraordinary could happen. Neutron stars are the collapsed cores of massive stars that have gone supernova. They are incredibly dense objects, packing more than the mass of our sun into a sphere only about 20 kilometers in diameter. The pressure inside a neutron star is so immense that it crushes atoms completely. Electrons are forced into protons, turning them into neutrons, creating a star made almost entirely of a dense sea of neutrons. But what happens if you keep adding pressure? The theory suggests that the neutrons themselves could be squeezed so tightly that they break down into their constituent up and down quarks. This creates a state of matter known as quark matter, a sort of soup of free-roaming quarks. Under these extreme conditions, it becomes energetically favorable for some of the up and down quarks to transform into strange quarks. Why would this happen? It's a matter of basic physics, specifically the Pauli exclusion principle. This principle states that no 2 identical fermions, like quarks, can occupy the same quantum state at the same time. In a dense soup of only up and down quarks, the particles are forced into higher and higher energy levels because all the lower energy slots are already filled. This makes the system very energetic and unstable. And by converting some of the up and down quarks into strange quarks, the system can relieve some of this pressure. The new strange quarks can occupy the lower energy states that were unavailable to the up and down quarks. This lowers the overall energy of the system, making it more stable. This mixture of up, down, and strange quarks in roughly equal numbers is what we call strange matter. The strange matter hypothesis takes this one step further. It proposes that this configuration isn't just stable under extreme pressure. It's the most stable form of matter in the universe, even more stable than the atomic nuclei that make up our world. If this hypothesis is true, it means that strange matter is the true ground state of matter. This implies that all the ordinary matter around us is actually in a metastable state. Like a ball perched precariously on the top of a hill, just waiting for a nudge to roll down to a more stable position at the bottom. The strangelet would be that nudge. A strangelet is a hypothetical droplet of strange matter, varying in size from as small as an atomic nucleus to much larger. If the strange matter hypothesis is correct, then even a tiny strangelet would be perfectly stable on its own, capable of existing outside the crushing pressure of a neutron star. If such a strangelet were to encounter ordinary matter, like the nucleus of an atom, its stability would be overwhelming. The strong nuclear force would pull the ordinary nucleus into the strangelet, and the intense energy environment inside would trigger the conversion of its up and down quarks into strange quarks. The original nucleus would be assimilated, and the strangelet would grow slightly larger. This process would be catalytic and self-sustaining. The now slightly larger strangelet would then encounter another nucleus, and another, converting each one and growing exponentially. It would be a relentless, unstoppable chain reaction. The conversion releases a huge amount of energy, which is why the end result would be a hot, dense lump of strange goo. If a strangelet hit Earth, it would be an extinction-level event unlike any other. It wouldn't be an explosion in the conventional sense, but a phase transition, a fundamental change in the state of matter itself. The process would likely start at the point of impact and spread outwards, consuming the planet from the inside out. The entire Earth, with its mountains, oceans, and life, would be converted into a perfectly uniform sphere of strange matter, glowing hot from the energy released during the conversion. So, where would these planet-destroying particles come from? The most likely source would be collisions between neutron stars. When two of these ultra-dense objects spiral into each other and merge, the event is so violent that it can spew debris across the cosmos. If these neutron stars contain strange matter in their cores, then this collision could scatter tiny strangelets across space, sending them hurtling in all directions at near the speed of light. Another possibility is the formation of strangelets in the early universe, shortly after the Big Bang, though this is considered less likely. Given these terrifying possibilities, it's natural to ask, why haven't we been destroyed yet? Strangelets exist and are zipping through the cosmos. Surely one would have hit us by now. The universe has been around for 13.8 billion years, which is plenty of time for such an event to occur. The fact that Earth and powerful argument against the existence of dangerous strangelets. If they were common, the moon's surface would be peppered with evidence of strangelet impacts, or the moon itself would have been converted long ago. Furthermore, scientists have been conducting experiments in particle accelerators like the Relativistic Heavy Ion Collider (RHIC) for years. These machines smash heavy atomic nuclei together at incredible speeds, briefly recreating conditions similar to the early universe or the cores of neutron stars. There were initial concerns that these experiments could accidentally create a stable strangelet that would then destroy the Earth. However, extensive safety reviews concluded that the risk is virtually non-existent. The energy levels in these collisions are actually lower than those of cosmic rays that have been bombarding Earth and other celestial bodies for billions of years without any catastrophic consequences. If cosmic ray impacts can't create dangerous strangelets, then our particle accelerators are highly unlikely to do so either. The prevailing view is that if strange matter does exist, it likely only exists under the immense pressure of neutron star cores. It's probably not absolutely stable, meaning if a piece of it were to escape into the vacuum of space, it would quickly decay back into ordinary matter. It might be stable inside a star, but not outside of it. This would mean that strange matter is a fascinating, exotic state of matter, but not an existential threat. It's an intriguing puzzle in astrophysics, a key to understanding the inner workings of some of the most extreme objects in the universe. However, the strange matter hypothesis has not been definitively disproven. It remains a tantalizing and slightly unsettling possibility at the fringes of our understanding. The universe is filled with wonders we are only just beginning to comprehend. Strange matter is a perfect example of how our quest for knowledge pushes the boundaries of our imagination, leading us to contemplate concepts that are both inspiring and terrifying. It reminds us that beneath the familiar surface of reality, the fundamental laws of physics may allow for possibilities stranger than we can possibly imagine. Thank you for joining us on this journey into the heart of strange matter. To explore more cosmic mysteries and mind-bending physics, make sure to follow us at Space